Bo Iversen is professor of chemistry at the Aarhus University. He is William investigator, director of the Aarhus University Center for Integrated Materials Research, IMAT. And the most important, Bo is general secretary and treasurer of the IUCR, which means that the whole money for crystallography worldwide goes through his hands and pockets. He obtained his PhD degree from Aarhus University in 1995. And following a postdoc period at the University of California in Santa Barbara, he returned to Aarhus University in 1998 and became the full professor and chair of inorganic chemistry in 2004. Bo is one of a few Danish scientists holding both a Doctor of Science degree and Doctor of Technology degree. Bo is PI on the Dan-Max and Syncris beamline projects at Max 4. He's the fellow of the Royal Danish Academy of Sciences of Science and Letters. And among his awards, one can find the Queen Margaret II Science Prize, the Danish Elite Researcher Award, the Foss Prize, and the Aarhus University Science Prize. Bo was knighted by Queen Margaret II in 2015. So, Sir Bo Iversen has been single responsible supervisor on 57 PhD degrees. Can you imagine this? I was on 20, and I can tell you how difficult it is. And 90 master degrees and 87 bachelor degrees. So this is the whole army of scientists scattered all over the world, not only in Denmark. More than 550 peer-reviewed papers. Bo Iversen will talk today on chemical bonding and local order. Bo, the screen is yours.
All right. I hope you can see my slides. And thank you very much, Christoph. And thank you to Paulina for this invitation. I just want to say it's a wonderful initiative you've done in this commission. And also it's quite exciting to be talking here together with Simon, because he's, of course, one of the people who got me interested in the diffuse scattering. So my talk today will try and start in the chemical bonding quantum crystallography, and then move into Simon's world of disorder and diffuse scattering. But let me just start here. In the community of quantum crystallography, of course, knows Bragg diffraction very well. And when we measure these intensities in Bragg diffraction, the intensity, of course, is proportional to the structure factor squared. And these structure factors are Fourier coefficients of the electron density in the crystal. So the model we all use in crystallography, in Bragg crystallography, is that we say that the unit cell is made up of atoms. And if these are spherical atoms, we can then write this usual structure factor expression that's well known and behind all the millions of structures that have been solved. So this is how it looks when you have a result in crystallography, right? You have the average atomic positions and the thermal vibrations. And so what you see here is a spatial and temporal average of the crystal structure. Of course, this model forgets chemistry and why we are here, right? Because the world is not made of free spherical atoms. So if we subtract that model from the measured data, we of course see all the reorganization of charge due to chemistry. And here's an example of melamine that we published earlier this year. You see the beautiful covalent bonding effects. Now, in crystallography, about 50 years, Bob Stewart and then Phil Coppens and Hirschfeld and others then said, okay, can't we parameterize this electron density? And this was the multipole model. So we introduced a lot of parameters to try to describe both the transfer of charges and also the asphericity of the electron density. And this multipole model, of course, then if you use it, you can model your data and you get just the noise left down here after you have the multipole model. Now, I will start this my very first 50 years ago, my very first study was this study of copper Totten salt, which is a copper ion with 6 waters around it, then an ammonia and a sulfate. And I spent a couple of months measuring these point detector data at 9 Kelvin with my supervisor, Finn Larsen. And what you could see is this Jahn-Teller distorted copper site. And you could see the chemical bonding here, that the electron distribution has a hole because of the Jahn-Teller distortion in this X minus y squared. It was beautiful seen here. And of course, this started my career in electron densities. But later, a few years later, around the same time, Bob Stewart started also introducing Richard Bader's theory of atoms and molecules, and this became the way we, for a number of years, interpreted these experimental electron densities using the basic observer of the electron density. I will not go more into detail, but I probably mentioned it a few times. So I will start this talk by having 5 slides or so of typical examples of electron densities, just to give a flavor of what type of studies we have been doing and what type of studies can be done if you measure very good Bragg data and use the multipole model to get the X-ray electron density. So the first example here is something that we worked on a lot, I should say, in 15 years ago. So we discovered that iron antimonide has this gigantic thermal power, what is also called a Seebeck coefficient. So normally you would measure this in microvolts, but here it's actually in millivolts. So it's 3 orders of magnitude larger than normal, and we called it colossal Seebeck coefficient. And there's been lots, and we spent 5 years at least on this, and many others did as well. But one could ask, so iron antimonide, what's the chemical bonding in iron antimonide? And this, of course, is a marcasite structure. So it's been studied also by the giants. It's a famous structure in solid state science. And good enough, already 50 years ago, he wrote it up as a very, the orbitals in a very ligand field model, which gave a very specific ordering, but also suggests a very ionic structure. Later, Hoffman looked at it as a single phase, where you have an anionic antimony network and then iron cations donating electrons. This model gave an extra antimony bond, so you have like this ladder structure going up through the structure. You can, of course, ask the crystal itself and measure the data, and then you see that none of this is really correct. And really, there are many details here, but one of the things is that if you look at the atoms, they're virtually neutral. And really, the chemical bonding is looked at like a covalent network. So something in between the 2 other models. And I think this is a very good example that you cannot use the gas phase electronegativity concepts that we learn in chemistry when you look in the solid state. And if people don't know Martin Rahm's work on this, I think you should look it up. It's really, really wonderful work. Another example of these inorganic solids is titanium disulfide. A typical example of these van der Waals 2D materials, like graphene or molybdenum disulfide. Here you have titanium disulfide, which was the very first lithium-ion battery. And here you have the van der Waals layer gap here, and of course the gap here determines a lot of the properties, like the band gap. So a question is, what's the chemical bonding across a van der Waals gap? And we tried also to model this with all the DFT. We could all the van der Waals functionals, and you can see none of them can really reproduce the covalency or electron sharing we see by the X-ray experiment. So here is an example where you can say that measuring the actual data also gives some good feedback to theory to try to optimize the theory. And currently, it's not really possible to get it correct. Then my favorite example is maybe magnesium antimonide, because we discovered this about more than 10 years ago, and this is a fantastic N-type thermoelectric, and it's cheap and benign. And this magnesium antimony structure is the same as in solid state science, these 1,2,2 calcium aluminum silicate structures. Where you have and they're thought as single solids again, so a negative framework here with positive cations donating into it. But this view, of course, if you then go and actually measure the electron density here for comparison, I've taken tin disulfide. It could be titanium, you see before here. You have the van der Waals layer, so basically it's the same structure. You just added these magnesium 2 cations into this layer. And when you do the electron density and analyze the chemical bonding, you'll see that the 2 magnesium atoms in the structure are virtually the same. So they have approximately the same charge. The chemical bonding is kind of the same. So this is clearly not a single phase, this magnesium antimonide. And of course, this is the conclusion you would say here is that if you were a structural chemist just looking at the positions, you would not really get the true structure or the true view of it. One thing that really nailed it was that if we look at the thermal conductivity or the anisotropy of the thermal conductivity, then it's almost an isotropic compound. So the thermal conductivity is really like a network structure. It's not a layer structure like the ones up here. Okay, I thought I would also just quickly mention that in electron density, you can also get, of course, the electrostatic properties. This is a 20-year-old study. I still like it very much because at that time, I thought it was one of the biggest studies done, biggest molecules. It's like 272 atoms and 8 chromium atoms. And at least 20 years ago, that was a good demonstration of synchrotron radiation that I really like. And you can, of course, if you get the electron density, you can plot the electrostatic potential. And in here, it was very clear that you have this negative cavity and the positive periphery. And we then synthesized 5 different compounds to see how the guest inclusion would be in such a host structure. And the guest atoms, for instance, here put the negative oxygen away from the negative center of the host molecule. And in all those 5 cases, we from the electrostatic potential could at least give a first prediction of guest positions. If we look again on electrostatics, here's another example, 2 papers on the hydroquinone. This is something that Mark Spackman told me about, these hydroquinones. You know, they are benign organic molecule, but in the solid state, they suddenly form these wonderful clathrates where you can have guest molecules inside. And again, we could use the electrostatic potential to see if we can say something about how it looks into the cavity. And this structure, in this one, it was acetonitrile we had in the structure. And when you compare so we also did with acetonitrile, we did both X-ray neutron, and in the empty host, we just had X-rays. And if you compare the electrostatic potential, you can see there's a very clear difference. So what happens when acetonitrile goes in here? It actually polarizes the host structure. And this may not sound so much, but it means, if you're trying to do molecular modeling and come in with a guest atom into a protein cavity or something like this, you need to be able to polarize, have polarizable force fields. And finally, only a few years ago, also XN measurements. This is an 18 crown host where there are 5 different urea molecules inside. And this was an example to try to show how big are the electric fields inside crystals. And they're really gigantic, gigavolts per meter. And this is why these guest molecules, and they polarize each other. It's really an enormous, much, much more that we can make in the lab. So here's an example of what it does to the molecule. If you take a gas phase calculation, the dipole moment will be about 3.5. But once you're in the crystal, it's actually doubled. And there are many other aspects, but it's just to show you how you can use the density for electrostatic properties. And finally, just chemical bonding, of course, is also what determines material properties. And one example of this is MOFs. And this is a nice area of MOF literature. I think these glass-forming MOFs that normally you'd think an organic thing would just decompose when you heat it up, but you have these special MOFs that can actually melt, and then you can cool them down and you have a glass. So in one example here is these SIFs, so the zeolite imidazole frameworks. If you heat them up, they first lose their solvent, and then they become amorphous. And then you're saying, okay, then they probably start decomposing. But no, they recrystallize again in a new, very dense structure that in the literature is called the ZNI structures. And then this structure melts. And then if you cool that, you have a glass. And then only then it eventually here. So this famous, I think really in this field, very important study showed that as you heat it up in the melt, basically the structure is preserved. And the chemical bonding used, and this is the 1D PDF that shows the chemical bonding preserved. Now, we then we made the crystals of two structures, one with the zinc and one with cobalt, and they're completely isostructural. So the bond lengths are within 2,000ths of an angstrom, and the angles are something like a few degrees different. So if you're a structural chemist, these are identical compounds. So it's very hard to understand why the zinc structure melts and the cobalt structure decomposes. But if you look at the electron density again, you'll see that in the cobalt system, you have a much more covalent situation. This covalence between the metal and the ligand destabilizes the linker. And this is why this one decomposes, whereas the more ionic bonding situation gives you the melt that is so well studied over here. So this is some examples of electron density studies, and now I'll slowly move into this thing that everything is not perfect in crystals, like we think when we do the electron density. And to explain this, I can go back to maybe my very first study, the copper Totten salt study. If you measure at low temperature, you'll see that it has the Chantelli distortion, right? So there are two short copper-oxygen bonds and one long copper-oxygen bond about 2.30. But then as you start heating this system, you see that one bond gets shorter and shorter, and the other one gets, when you do your least squares refinement with spherical atom, this one gets longer and longer. And you'd say, what is going on here? And it turns out the copper Totten salt is a famous example of what's called a Mexican hat potential. So if you have the isolated copper ion here with the 6 waters, you will have a potential surface where you can elongate in each of the Chantelli axes. And they would have the same energy, but when you're inside the crystal, there is not a isotropy, so the elongation in different directions will have different energies. And it turns out here that the O7 has the lowest energy. So at lowest temperature, this is the structure we measured in my charge density study. But then as we heat up, we start populating also some molecules where the O8 is stretched. And this is why we see this apparent bond length change. So really it is the average structure over the crystal really just has two components on each oxygen side. And in structural crystallography, this is of course very well known that you just add two sites and you have an occupancy and you can refinement. And this is all very nice. But my point to bring home is that, of course, the average structure I do here in Bragg diffraction do reflect the actual disorder by having these very, very elongated ellipsoids if we model them just in the center. So it's a wonderful structure, and I can talk. My students always laugh about it because I guess it's my first study, so I always loved copper Totten salt. But if you look at the BDF, then of course, then there will at any given time always be two short bonds and one long bond. So if the 1D PDF down here, you'll see two bonds that are 2 angstrom and one that's 2.3 angstrom. And if you look, this is 100 Kelvin synchrotron data from Spring 8. You can see that the diffuse scattering here is really minor. It's just going out from the center, but there's nothing really correlated diffuse scattering in this structure. So if we look at this famous review by Dave Keenan and Andrew Goodwin, where we put this example of a water crystal, right? Then if we have perfect order, we have the Bragg diffraction. But then if we now invoke hydrogen bonding, you'll see there will be some local structures correlation that will give diffuse scattering. And of course, if these water molecules just don't feel each other, then we have this diffuse scattering going out here. So this is the example of copper Totten salt. Basically, we have no correlated disorder between the unit cell. The chemical bonding that's driving this Chantelli distortion is, you can say, intramolecular. So an important point is the average structure reflects the disorder, but it doesn't really reveal the local structure. So we don't see the 2 oxygen positions in the average structure. It's just something we interpret. So we need some tools to actually see the true local structure. And my first example here is copper selenide, which is really, I do a lot of thermoelectrics. So a lot of examples will come from thermoelectrics. And copper selenide was almost going to space, right? It was really, really heavily studied by NASA in the 60s. But the problem is it has very high ionic conductivity, so it deteriorates, and it was never chosen for the missions. But it has been very, very studied, basically. And if you look at the crystal structures of copper selenide, you can pick any space group or any crystal system you want. If you're diplomatic, you just say there's a lack of agreement. But in all crystallography, it's about crystals, and a lot of our activities are centered on synthesis. And in this case, we were able to do a gas transport synthesis and get quite decent crystals, and then measure some nice Bragg diffraction data here. And from the Bragg diffraction, we could refine the average structure, and it's highly disordered on the different copper sites. So you see, you have like a copper-rich layer and a copper-deficient layer. And then on each of the copper sites, you have multiple occupancies. But it was also clear from these data, if you look up here with the circle, that there were extra Bragg spots that, or looked like Bragg spots that were not indexed by the unit cell. So it looked like it had a superstructure. But when we don't really know the structure, we can always do the maximum entropy, which is a method I also worked on since I was a student. And here you just divide the unit cell into voxels, and then you distribute the electron density under the constraint of the data and this maximum entropy. And when we do this through the phase transition with the single crystal data, we see that we get copper moving from the rich layer down to this poor layer, and in the end we get into this anti-fluoride structure, which is highly, highly disordered, and this is where it's been studied a lot, this subionic conductor copper selenide. But in reality, these are not Bragg spots. So I had a new student at this point, Nikolai Roth, and he took the crystals to spring 8, and yes, you could see extra spots in the layer, but when you look perpendicular, these spots are really just a cut through these very, very diffuse rods. So there's clearly disorder in copper selenide. And this is where we then have to generalize our crystallography a bit. I think most crystallographers are known to know the Patterson function, which is the Fourier transform of the Bragg peaks, right? But if you instead Fourier transform the diffuse scattering, you get this other correlation function that we call the 3D delta PDF. And the delta here is because we can write the electron density as a periodic density plus the difference to this periodic density. And the diffuse scattering will then be the correlation function on this difference to the average density. And when you do this on copper selenide, you get these in the plane beautiful with correlations to very, very high R values, whereas in the C direction here, perpendicular, they die out very, very fast. So clearly you have these rods are due to the disorder along the C axis. Now, Nikolai then said, okay, can't I solve the structure? And he then said, okay, I can use my 3D PDF. And if I choose an origin, then of course I'm autocorrelated with myself. But then I'm negative just around. And that's, of course, if the copper atom is here, then you can't have two atoms here in the disordered structures. So the true structure must just have one copper atom. And then you could look at the vectors here. So can I have a copper atom here? But it's negative. That means that there's less density than in the average structure. So that's not where the copper is. How about this side? It's also negative. So that's not where it is. But in this side, you have a positive. So there's more density than the average. So this is where the copper atom is. And this way, Nikolai could solve the whole structure. And this is for this copper atom, the layer structure. And he could do that for all the layers. And it turns out then the copper selenide is basically just these slabs that are perfectly ordered. And then these slabs are disordered along the C-axis. So they can be inverted and they can slide. But this is the true local structure of a copper selenide. And you can then say, have I learned anything at all? And one of the things, because, you know, I think this is very important that diffuse scattering should not just be some mathematical discipline. We should actually try to learn about our structures. And one thing that's clear here is that in the true structure, you have a copper-copper dimer that you wouldn't see in the average structure in the distances. So this is could be a chemical bonding feature that is really forming this local structure. We are looking at the high temperature subionic conductor because this is one of the best examples of subionic conductors, highly, highly anharmonic and highly, highly distorted copper that can just zoom through the structure. Here we also have some nice diffuse scattering, and we can get the 3D delta PDF, but this paper is currently under review. So the next example is indium telluride, which is also thermoelectric, studied a lot in the thermoelectric community. And this looks like a very simple structure, just indium and tellurium. But when you look at it, it has this wonderful one-dimensional structure. So in these, you have these chains of indium 1+ atoms, and then you have the tetrahedra of indium 3 and tellurium also running down the axis. And what is really funky about indium telluride, it has this weird thermal conductivity. And this is one of the things I always look for in studies, you know, do you have a low thermal or weird thermal conductivity? And here it's both very low and also a very weird temperature dependence. So let's look a bit more on this structure as kind of the logic in our studies. And then we go to spring 8 as usually. We want the best data we can get, and BL02B2 and then or B1, sorry, and then we measure the Bragg diffraction here on some single crystals, and we could see these are the MEM density and the nice big peaks from the indium 1+ along these chains. But then we also see these secondary maxima. So in between you have these interstitial sites, and showing that there is disorder on the indium 1+ position. Now, if we add these into our normal structural refinement, we can see that we can get the R value to drop to about 1/2. So clearly the data like this disordered model, and also it just shows that both the main site and these secondary sites are very disordered, and this of course affects the thermal conductivity. We did measure the single crystal data up in temperature, and we see this really wonderful transition from having separate sites of the disorder to basically getting this sausage through the structure. So what you see is this order-disorder transition as you heat up the sample, and then indium 1+ can zoom through these channels. So how about this should give diffuse scattering also, and indeed it does. It's not very strong, and there are some features one can interpret here, but I'll just draw the attention to this feature here, because this is one of the features that disappear as we heat up and get this sausage through the structure. So at low temperature, there is this 5.8 angstrom correlation, and this is because basically if I have an indium atom at this site, then I also have an indium atom at this site. But as we heat up, then the correlation disappears, and I just have a totally disordered sausage through the structure. So, but again, why is this happening? And the whole point here is a matter that I have studied, and many others studied, the stereoactive lone pairs in the charge density community. It's sometimes also called metavalent bonding. But the idea here, of course, is that the lone pairs on indium or lead or tin can hybridize with the anion orbitals, and this gives a very strong coupling for electron-phonon coupling, and gives these highly anharmonic systems. But I will not talk more about that. I'll instead just point out to another system that has been studied tremendously in thermoelectrics, the most famous thermoelectric, lead telluride, because lead also has these stereoactive lone pairs 6s electrons, and this is what's behind this very strange behavior. And this is where this is Simon's famous science paper from 2010 and Emil Bosin, right? That basically said from the analysis of the 1D PDF here, you could see that it must be that lead seems to be or is off-centered from the sodium chloride lattice position, and it has a temperature dependence. And this, of course, intrigued me also, because this is, a heavy lead atom that's off in a very simple structure, and this can explain why the thermal conductivity is so low. But you can then ask, is this disorder static or dynamic? And this has a number of papers, but I think the one that really nailed it is this one, again from the same group of authors, right? But this time based on single crystal X-ray diffraction, you see the beautiful diffuse scattering. And all this diffuse scattering can be modeled as thermal diffuse scattering using the Yale program of Arkady Simonov, where you get these correlation coefficients. So all is well. We didn't get there in time with these studies. We also spent a lot of time working on lead telluride and did the 3D PDF and Spring 8 data. Here in these papers, we did it up in temperature, and you could see how the correlation. So these are, of course, all driven by the phonons, and it's very nice represented in the thermal diffuse scattering. And it was also nice to compare it to something where you don't have a stereoactive lone pair and potassium chloride, but you can read more if you want in these papers. Now, I said that one thing, the average structure represents the local structure, but there's a really intriguing concept that has been introduced in the diffuse scattering community, and this is this thing with hidden structures. I don't know who, I think it's Andrew Goodwin who came up with it, but But one good example of hidden structures are the half-Heusler compounds. And half-Heusler have been extremely studied in thermoelectric. They're also very popular as topological insulators. And, it's like this type of structures that are everywhere, like the perovskites. You can use them probably to wipe your floor or whatever. But so they're everywhere. And one of the concepts that has been constant is this, that they should follow Sintel chemistry. And in fact, in thermoelectrics, this Sintel concept just keeps coming up and up and up. Everything can be explained by Sintel. And again, it is an anionic network with a positive cation. So half-Heuslers is basically a diamond lattice, the purple here, and then in the octahedral holes of the cubic close packing, you have these cations that donate into the negative network. And if we have transition metals in there, we have the A-twin electron rule. So for titanium, copper, antimony, you'll have A-twin electrons this way. So you have a negative framework and a positive titanium atom. Now, then, of course, in thermoelectrics, people will say, okay, you say the A-twin electron rule, so what if I give it 19 electrons? So I put niobium in there. And then the structure it comes back, at least that was the initial thinking, no, I don't want 19 electrons. I want to be a Sintel phase, so I just make vacancies. So I have 0.2 or 20% vacancies, and then I can still follow my 18 electron rule. And this was kind of the thinking for a couple of years, but we then started synthesizing different kinds of these half-Heuslers with niobium, the 19 electron half-Heuslers. We used different methods. One where we slowly cooled it, basically, so we could get a distribution of vacancies that was maybe in the ground state. And then we did various thermal quenches where we could then maybe get a higher energy state. And clearly the two crystal structures are here's one quenched and here's one slowly cooled. And you see the diffuse scattering here is obviously very, very different. But if you do the Bragg scattering, then it's interesting, because then you get the exact same structure from these two crystals. All the samples we have done, the 5 samples, always have 1/6 vacancies. So the occupancy of niobium always comes out to 1/6. And the Bragg scattering and the refinement are basically identical. So if you were a structural chemist doing Bragg scattering, you'll say these crystals are identical. But clearly they are not, right? I mean, they have very, very different diffuse scattering. So what's going on? And then Nikolai, the brilliant student I had, he said, okay, what if the vacancies want to avoid each other? So there's a penalty if I put vacancies next to each other or next nearest neighbors. And in fact, you can make a fully ordered structure where you never have vacancies nearest neighbor or next nearest neighbor. So we can just make some kind of energy function and saying, if this is 0, then, I have no next nearest or nearest neighbors, but then we have this penalty. And then you can start doing a simulation of different structures. And when you do this, you can exactly reproduce the diffuse scattering that we measure in the different crystals. So what these things say, first of all, again, please do not use the Sintel model for this, because all the structures have x equal to 1/6, they do not have 20% vacancies. The structure really wants to have the vacancies avoid each other. It's not about the stoichiometry. And the second thing is you can say, okay, so you now know that something that's not there avoids something that's not there. That's really not chemical understanding. It's just purely describing the diffuse scattering. So you can say, how is the structural response actually? What is the local structure around these vacancies? And of course, if you look at the residual density, you then see extra peaks around antimony. Okay, so we just saw for copper tungsten. Okay, I just put an extra antimony site and have a disorder in my antimony. That's all very fine, and I can refine how far the antimony moves away, and it is about 0.14 angstroms. I can see the exact same thing if I do the 3D delta PDF. Then if I have a niobium atom, then there's a negative, so there tends to not be an antimony. Or conversely, if there's a vacancy here in the middle, then antimony will move towards the vacancy. So all is very good. So you have this relaxation around the defects that's really, then you're approaching at least the true chemistry. But then you'll ask, so what's the point? Again, what you really want is to relate the local structure to thermoelectric properties. And then you can look in the literature. C et al. They made these samples with a lot of different nominal content of antimony or niobium. And you'll see as soon as you get above the 16/1/6, then you start to have impurities. So the structure wants to always keep 1/6. And indeed, all the samples have the same unit cell. So, but then if you compare all the structures with the same unit cell but different but different x's here, you see about 15% change in lattice thermal conductivity. So distributing your vacancies can actually increase the ZT of this compound by 15% just by playing by the local order. If you want further chemical bonding analysis, I know I'm in a quantum crystallography talk, then please read this paper by Kasper Tolborg, where he did the overlap of the, and looked at the chemical bonding. So how Sintel-like it is, what is the overlap covalency in the Y set, and how big is it in XY? And you would say that Sintel is when there's very little overlap with X and Y, but a lot between Y and Z. But they are really horrible thermoelectrics. All the good Heisler structures, they are the non-Sintel ones sitting up here. So using simple bonding models is maybe not so fruitful. Okay, you can do X-ray scattering to get diffuse scattering. You can also do neutrons, and then it gets a little more tricky, because if you Fourier transform your diffuse neutron scattering, then you get the magnetization density. And Nicolai then wrote it all up mathematically and said, okay, if I write the magnetization as a periodic function plus a difference, then the correlation I get when I Fourier transform is this more complicated thing. And now, of course, magnetization is also a vector. But if you're lucky, if you're lucky, then you will have no periodic density. So if you have a frustrated magnet, then this goes away. And if you also have a cubic system, this horrible factor goes away. And then you can just left with this one interpreting whether you have antiferromagnetic or ferromagnetic correlations. And one example is Bixbyite on this. This is a natural sample from Utah where you have a disorder on the iron end. So it's iron 2, oxygen 3 is the base formula, but this is mixture with iron and manganese. You have two metal sites, one quite octahedral, one very distorted. And the trick here we then did was basically we measured the neutron data at room temperature and then cooled it down when we get the magnetic diffuse scattering. But then you can subtract the structural disorder from this map, and then you end up just with the magnetic diffuse scattering in the system. And this you can Fourier transform, and what you then see is then your correlations, magnetic correlations. So Nicolai, of course, did his game again. You sit here on one atom, and then what is the correlation to the next one? And you see this is antiferromagnetic, so the closest one tends to be antiferromagnetic. Then the next layers tends to be ferromagnetic, and so on. The third one tends to be antiferromagnetic. And you can do a lot of analysis on this, and I'll just come back to that. But of course, this structure also has structural disorder because you have the iron manganese sites. And this is very, very hard with X-rays to distinguish between iron and manganese, but with neutrons, you of course have negative and positive scattering lengths. So if you do the single crystal X-rays, you see these, I think you can see here, these long rods going down. So we are back in the same, copper selenide. There's probably some 2D order with 1D disorder. Whereas in the neutron diffuse scattering, you see this very, very slow varying, very broad diffuse scattering. So that's probably some short range order that gives rise to this. But then you can do your residual density from the X-ray refinements, and you see, there are some extra peaks near the metal sites. You can refine it, as I said, did before. It gives about 7% occupancy. But what is really the structure of Bixbyite? Well, the electron diffraction has showed that really Bixbyite, when it's from natural sources, will have these inclusions of another mineral called brownite, so this manganese silicate. And the thing is that Bixbyite and brownite has almost the same A-axis and then just a doubling of the C-axis. So what the crystal basically does, if you look at the structure here, the A1 layer of Bixbyite is virtually identical to the A1 layer in brownite. And again, one of these three layers are virtually identical. So when the crystal grows and then you maybe have a silicon matrix around it, then it gets confused and gets this inclusion of brownite. And then when you're depleted, you probably go back and make Bixbyite. And these are about 2 nanometers, these intergrowth. So another student, Christopher here, brilliant student, he then said, okay, let me try to simulate it. And then he just said, okay, with some percentage chance, I will see the brownite layer. And then he built these gigantic 10 by 10 by 400 supercells and then simulated these brownite intergrowth. And the scattering you get from this model is then exactly identical to the diffuse scattering that you measure. And then you can say, okay, what about these residual density features? Because one thing I say is that the average density should also show disorder. And in fact, if you condense all these many supercells down, you get exactly extra density around the metal sites where we refined it. So I think this model is correct. Then how about the neutron diffuse scattering? Well, there it can either be the correlations because there's some local ordering of the manganese and iron, or it can be because the oxygen bond lengths are different for iron and manganese. And it's the latter here that really, and I'll show you the model here, but you can see the model we get out of this local order describes the diffuse scattering very well. And here it's my link is to the chemical bonding again, because if you have in a very octahedral site, then iron 3, of course, has an extra electron compared to the manganese. So this means there's an extra electron in the anti-bonding, and this is destabilized, and I'll expect the iron-oxygen bond to be longer than the manganese-oxygen. If you take the highly distorted site here, then you will tend to have a Jahn-Teller distortion for the manganese, but not for the iron 3+. So here the actual bond is probably longer for the manganese, whereas the ones in the planes are the same. So one can write off and say, okay, now I sit on my oxygen, what is my metal bond lengths, and make these coefficients and try to refine them, and then you get exactly this diffuse scattering as seen before. So this is the chemical bonding that basically drives the diffuse scattering. But more importantly, when you move the oxygens around, of course, you change the super exchange pathways through the structure. So by introducing the manganese and iron here disorder, you also change the magnetism. So of course, ultimately, it would be fantastic if this is really a handle to tune the magnetism. We've not been able to synthesize these. These are all natural crystals. It's not so easy to make big crystals of big spirit. But I will be, Christoph, what is my timing? 5 minutes?
Yeah, 5 minutes, the longest.
Okay, so 2 minutes. I'll just quickly breeze through this. So Spinel is just another example, again, a frustrated magnet. It's a normal Spinel zinc iron oxide, and then iron, the magnetic atoms sit on this pyrochlor lattice, the B lattice of Spinel. And you can do the same. You can spend 2 years like Jonas did here to really grow these jewels of crystals. And then you can measure the diffuse scattering, and you can do the magnetic 3D delta PDF again and look at how the magnetic correlations. What you see here is that in this pyrochlor lattice, you kind of get a ferromagnetic core where you have primary, in the third nearest neighbor, you have antiferromagnetic correlations. One thing that's contrasting big spirit and Spinel is that if I integrate my 3D diffuse 3D delta PDF, then in big spirit all the peaks have approximately the same temperature dependence, whereas in Spinel some of the peaks go from negative, so antiferromagnetic to ferromagnetic, and it's really, really funky. So the magnetism, the orbital interactions here behind the actual magnetism must be very, very sensitive to changes in the geometry. Okay, so I'll finish here to make some conclusions. I spoke not so much about quantum crystallography in the chemical bonding sense, but I tried to bridge into this thing of disorder, which I think is highly important that we also take this into account. So, but if I just talk about the chemical bonding for sure, I think we sometimes forget in the field that X-ray electron densities are unique data. They are fantastically close to the wave function, and they are experimental data. And I think conclusions about chemical interactions from average atomic positions, they're not speculation because they're built on a lot of chemical knowledge, but I think many times they can be deceptive. And I also think in chemical bonding analysis, I would like to see more experimental efforts. I think there's a lot of effort spent on modeling and behind the computer, but maybe sometimes less in measuring very good data. And good data, it really is the starting point of everything here. When it comes to local order, I again would advocate, please, some of us go out and make crystals and measure data on real crystals. Again, we never get the model right anyway. And if you don't have real data, then, theory is just an opinion, right? So we need to calibrate. I think it would be wonderful if we can somehow bridge the fields of chemical bonding and get closer to understanding the chemical interactions that make the local order, because local order is such an incredible tool if we in material science, if we can start controlling it. So, but to do that, we need to understand why it happens, not just describe the effect. Then it's, this thing, I think simple models sometimes are not so good. They are sometimes, you misinterpret things, and I've given you some examples here. The simple model where I think maybe it's not so useful to use simple models. Finally, I hope that the end goal of this is that we can actually quantify effects of correlated disorder. If we can, and then basically see what does it, like we kind of did with the half-Heuslers, what does it matter with relation to materials properties, because then we have an entire new world opening up. So finally, I'll just, of course, thank my current group, and also you've seen many years of studies. So also I've absolutely wonderful research group I have these days, and I've had it for many, many years. The reason why I can run it is because of the Willem Foundation that supports me very, very generously, and they basically take the hard part out of it by just trusting me to do whatever I want to do, and this is really a privilege. So thanks a lot to Willem Foundation. And then finally, online, thank you to all for your attention.
Thank you very much, Bob, for excellent overview of really stunning results. So now the lecture is open for comments and questions.
We already have two questions posted by Roman Gaida. The first one is, how exactly you deal with electrons of block D of transition metals when you conduct multiple model refinement? Because it is a problem, I think.
Well, I mean, you have to have hexadecapoles, of course, in your multipole model if you want to model D electrons. But then I think the multipole model normally is okay to give a very low residual around the 3D metals, if that's what the question is. Whether you then can use it for something like in the early days, there was a lot of people who extracted d orbital populations with some kind of accuracy, right? Whether that's more accurate is probably less accurate than theory, right? But so what we do is basically just have a full multipole model. It depends on the data. Actually, some of the very early data we had to have a lot of radial flexibility to fit the data. But I think this comes back to the better you measure your data, the more you can say, right? So if you measure run-of-the-mill data, probably run-of-the-mill multipole refinement is fine. But if you really go to very low temperature and measure to very, very high order, then you can maybe see fine effects. I hope that answers the question.
And second question is, do you think that theoretically generated dynamical structure factors, dynamical means including thermal motion, can give information comparable or even better than experimental intensities?
I don't know. I don't know which one is better here. Yeah, I don't know if anyone out there is more qualified to say what's the quality of these. I think it depends a lot. So dynamic structure factors, you still mean Bragg diffraction, right? You don't need. Is that correct?
Yeah, probably. Yeah.
Yeah. Okay. I think the experimental data, especially if you have weak interactions, can say something that theory has a hard time getting, because theory is not good at weak interactions, right? It optimizes the energy. So, for instance, these van der Waal interactions, I think experiment can show things that are hard to show by theory. And then, of course, if you have things like MOFs, theory is really not doing very well on MOFs, right? I think experiment is clearly better when you have these kind of hybrid inorganic organic structures. So it depends on your system, I would say. You have, of course, but that's the same in every field of science. You have to choose your studies well, right, so that you can say something new. Probably you can find a lot of studies where theory will do basically the same as experiment, but you can certainly also do the others. And even in that sense, I still have, as an experimentalist, we have to measure things, right? I mean, otherwise we never discover anything. If we just model the world as we think it is, what's the point? I think we actually have to study the world that is it is, not as we think it is.
We have a question from Simon Grabowski. For transition model containing compounds and synchrotron radiation, how frequently do you observe radiation damage, and how does it impact the subtle effects of electron distribution?
It's a good question, and I think no one has really solved this thing why certain transition metal crystals always decompose. So my colleague, or actually former colleague now, Jakob Overgaard, has had a lot of struggle with measuring on these molecular magnets, and there's been a lot of this radiation damage. I think that's a golden question to everyone in this community to really solve this thing why these transition metal complexes always die. Maybe that's why I study hard inorganic solids. You can throw them through the wall and nothing happens, right? That's so it's a good question. And it's clear that in many cases you do have radiation damage. And I think I've seen some talks. Someone is trying to chase this a bit systematically, but it is a real problem. Of course, I would also say that nowadays with when you don't have shutters and you just shoot on the crystals, right? I mean, you measure data within much shorter time than you did previously with the new detectors. So you're not you can measure even full electron density data in reasonable time. So experimentally, radiation damage is also getting less of a problem. But there is all these transition metal problems, and I think everyone in the field who has measured on them have seen radiation damage.
We have a question from Simon, but let me first.
Simon can ask question himself. Yes.
Yeah.
Hey, Bo. Thanks. It was a really thought. So I had a naive question because I don't really know the electron density stuff, but I just wanted to know. So when you solve the electron density, you're using the space group that's coming from the structural part, right? But the electron density you're interested in is the electron density of the valence electrons. And I wonder if there are interesting cases where the valence electrons can break symmetry without it changing the structural space group, and whether that's an issue.
I mean, I think this thing about what symmetry constraints you do in the modeling is an age-old one, going back even to the pioneers like Bob Stewart always say you should only have no symmetry constraints, and the other one is what does on your metal side, what is can you constrain the local symmetry there, so you remove some parameters. I don't know if I have a general. Anyone online knows a good example where you have.
Diamond is the first example when you have.
Yeah, but that's okay. But that's just because you don't have. I mean, in a spherical model, clearly you have a forbidden reflections, right? But and you have aspherical chemical bonding. Okay, yeah, that's a good example, right?
Yeah.
So diamond, the tetrahedral bonding, right, gives you the forbidden 422 and 222 reflections that you wouldn't see in a structural refinement.
And then what happens if you solve the electron density in both those space groups? Do you get a different result or different insights, or how does it change?
Well, in one you will get the chemical bonding. I think the other one you will not see it. If the isn't that right? I mean, if otherwise the forbidden reflections would be zero, and they're clearly not. So you would not observe the chemical bonding. But in transition metals, I don't know if we have had, not on top of my, but I think, a lot of people enforce a symmetry on their multipoles that is not there in the crystal. And this of course can give you, it's allowed to not follow some enforced symmetry that people do and this is just to save parameters. But again, that's another case. If you want to see this, you need the best possible data, right? Then you can see whether, if it's not enforced by locally the symmetry, then then you can have this breaking, as I understand you're asking for. But to see
Yeah.
it, you again need the very good data. I would once again, please go to lowest possible temperatures and use synchrotrons. When they are heavy elements, go to synchrotrons.
And then we have questions from Piero Mac.
Yeah, that's a good point. You have there, Piero, if I read your chat correctly.
Yeah,
That when you
I
have
do
two sender
put the
terms, then it's
microphone
actually easier.
writing a comment and then
agree on
probably,
that, yeah.
I think it's easily readable. What I meant is that in reality, in principle, modeling the d-block transition metals should be easier because the density is there mostly atom localized, like the atomic multiples,
Yeah.
whereas in molecules it's mostly diffuse, and so the atomic multiples is a much stronger approximation. Then in practice, we know that we have many more problems with transition metals, but just in terms of properly correcting for absorption, and as you mentioned, also the problem of the radiation damage. But theoretically, it should be easier with transition metals than with organic molecules.
You can say, I mean, and I guess this gets, if you want to interpret the individual multiples, if you just want the total density, then maybe it's okay. But I agree totally in principle that it should be easier.
Okay, thanks.
I don't see more questions written, but I have a question.
If I could have
Please go.
In the case of 3D PDF, how do you treat thermal motion? What do you do with thermal motion of atoms?
I mean, what do you mean? You have them refined in your crystal structure model, right? So there's thermal motion in there.
Okay,
but you mean if you mean TDS? So of course, as the
PDF, when you do per distribution function,
right?
What do you do with thermal motion?
I'm not sure. I mean, what do I do? I don't. I mean, if it's if you see modeling the diffuse scattering, then of course if it is the diffuse scattering is because of correlated motion, then you can use a Yale program that Simonov have produced, and you have this generalized correlated correlation factors, right? Then because that basically, like let telluride, it means that if I go this way and then you also go this way, I mean you have correlated thermal motion, and this gives you the diffuse scattering in lead telluride. This you can model explicitly, and the world expert of this is Arkady Simonov, right? He's written this Yale program to model that. We have used it. I mean, I have no other experience than what we have used the Yale program for.
Okay. In the case of inorganic crystal, we all got used to think in terms of polyhedra, and I think this is something what is shaping the whole field, whereas we are getting experimental electron densities. We can characterize atoms, ions better than in polyhedral representation. Maybe we should change our attitudes and simply start thinking in terms of atomic basins and properties of electron density rather than polyhedra and structure.
I think. I mean, obviously, I'm also brought up with polyhedra and close packings and things like this, right? They have their very, very strong points to condensed structures, right? But I also think that, for instance, magnesium antimonide, if you take that example, right, it's really deceptive. Everyone for 50 years had said this is a layered structure, right? So you can also get deceived by these simple models when you don't look actually at the chemical bonding. And this is where I say that if you just have the atomic positions, then anything you say about the chemical bonding in principle is speculation, right?
Yeah.
I mean, and of course it's correct most of the time. We know what hydrogen bonds do. We know what this and that, right? But in crystal, for instance, molecular crystals, I'm always very, very surprised how strong dispersion forces are. Yeah. And we sit and interpret some very small bonds, some halogen bond or something like this, but then you have dispersion interactions that are far bigger. And I think sometimes structural chemistry is too deceptive, right? We should be looking a bit more seriously at the actual chemical bonding.
Yeah. Okay, Paulina, sorry I interrupted you.
Yeah, that's okay. I have a question to how you model, how you build your model of for PDF analysis. So you are using spherical model to compute structure factors, and you have metallic centers with d electrons and clear aspherical features of electron density. Do you think that this will somehow, the lack of modeling of this, introduce some problems in the finding the correct positions of disordered atoms or the proportion of the disorder? Because the distance 0.1 angstrom.
But the chemical bonding effects are so localized in our space, right? So they're really far into, at very short R distances. I think actually in Versailles, Simon and I, we quickly chatted about this, whether you could. I would really love if you could see chemical bonding effects in the PDF, and I think one wonderful case could be amorphous carbon materials, right, where you never know if it's sp2 or sp3. But I also think that the difference here is so localized in our space that it's really hard, because there are all these corrections in PDF. So really seeing something that's, say, within. I mean, Simon is the person to ask here. He has so much more experience than I have, right? But so Simon, maybe you can answer. Have you ever really looked at non-spherical chemical bonding effects in PDF? I just think it will be really hard to see them. You have to measure enormously high up and trust your data down to your beam stop is removed. I don't know. Simon, what do you say?
Yeah, we haven't done that. I don't think it's completely out of the question. I mean, if you think in the context of 3D delta PDF, you have the delta means that you're taking a difference between what's actually measured from a model, and the model has the crystallographic symmetry because you're punching out the
and your model is spherical.
out the Bragg peaks, right? But if you, in principle, you could take a difference from a spherical atom model of the average structure, but you could also take a difference from electron density model of the average structure, right? And then you'd get actually a slightly different difference.
Yeah,
and
that's the question, whether you see the difference.
Is weighted by the set, right? So the atom, so yeah.
It's true there are a lot of corrections in PDF, and one of the corrections is this Morningstar Warren that we do. That's a very people get very upset about this one, but actually we found that it's not our worst correction, I would say. And that's the one where you're again assuming kind of a spherical atom approximation, and the intensity, the Debye-Waller factors kind of follow some average Q dependence. But the robust thing about
maybe do a theoretical 3D PDF here, and then just turn on some.
Maybe do diamond.
Yeah, and then
already came up.
Yeah.
Yeah, I'm not talking about the refining, the asphericity. I just switching to aspherical model to see whether it changed your interpretation.
I mean, the hidden structure thing in the PDF came about, and we've been studying this for many years.
Maybe I'm wrong sidling this.
Well, no, we didn't. We never called it that. We always call it like hidden broken local symmetries and things. But that came about because we were seeing them in the PDF and they weren't there in the models. And so my gut feeling about the electron density part and the chemical bonding part is that it's definitely there in the PDF. And if it's not there in our model, it's going to show up as an inability to fit. And then it's just a question of whether the signal that's there is strong enough and we have good enough signal to noise, and then obviously you have to have very, very good data, like Bo says. But I'm not aware of anyone who's really explored this, Paulina. Yeah, I think that's waiting to be done.
Okay, thank you.
Okay, as we do not see more questions nor comments, let us thank again Sir Bo for his excellent lecture.
Thank you.